The accumulation function is f. R1 is the derivative of f. It's the rate of change of f. R2 is the derivative of R1. Okay? It's the rate of change of the rate of change function. Okay, so what I'm showing you here for an x value of, so right here, I'm showing you the x value, current x value is negative 3.1, right here. And at that current value of negative 3.1, R2 is negative 7.2. So I have a couple questions for you here. What can you conclude about R1? So R2 is negative 7.2. So what can you conclude about R1? And then B says, based on that conclusion, there are two cases, R1. There's two possibilities for what you conclude about R1. And then what can you conclude about F with the given information that at x equals negative 3.1, R2 is negative 7.2. So talk about all that for a minute, see what you come up with. Go. Okay, so if R2 is negative, what about R1? Decreasing. Decreasing. Okay? So if a rate of change is negative, that means whatever you're taking the rate of change of must be decreasing. Okay? Even if it's a rate of change of a rate of change, it's still the same idea that if you've got a function, if its rate of change is negative, then that function is decreasing. That's what we have. We have a rate of change that's negative, so the function, in this case R1, is decreasing. So decreasing then, there's two possibilities. R1 is getting, if it's decreasing, less positive is one way that it could be decreasing, or more negative. So that means R1 could be positive or it could be negative. Even though it's decreasing, it could be positive, it could be negative. So can we conclude something about F in terms of, is F increasing or decreasing? Listen, R1 could be positive. R1 could be negative. So can we tell if F is increasing or decreasing? We cannot. But one thing, what can we do? What can we say? If the rate of change is decreasing, it's becoming what? Less positive or more negative, right? So think about those. Think about the relative size of change in y, or tangent lines. Tangent lines, less positive or more negative. So therefore, F is concave down. Concave down. Okay, now I'm going to show you the value of R1. So let's come up here. Let's actually show you the value of R1 here. Okay, so now I'm showing you R1 at negative 3.1, same point, and it's positive 7.44. So what can you conclude? Talk. Go. Okay, so knowing that the R2 was negative, we said that R1 could be getting less positive or more negative. Now we know. Which one is it? It must be getting less positive. And we can, right? Because it's positive. So if its rate is negative, it must be getting less positive. Okay? And so then we know it's concave down, but we can do even better than that now. So concave down just looks like this in general, but we could now narrow it down even further. The accumulation function must be the left side of that, because the rate is positive, I'm getting less positive, and that would be the left side of this. Does it make sense? Now that I've given you that the rate of change is positive, the accumulation must be going up, but getting less positive because the second derivative is negative. Okay, what about the value of the accumulation? Is the value of the accumulation negative or positive? Just the value of the accumulation itself at negative 3.1. If I plug negative 3.1 into F. Positive? Some are saying you can't know. You don't know. All we know is about rates. All we know is about the rates of F. We don't know a starting value of F. So the actual value of F, the accumulation, could be negative or it could be positive. All right, so I'm going to just move. Let's look at a different value of x. So let's go over here to x equals 2. There's x equal 2. Discuss. What's happening? Go. Okay. Is R1, well, I'm showing you R1, right? So, value of R2. So, from the value of R2, it's negative 3.3. So, what can you say about R1? Can you say from that it's positive, negative, increasing, or decreasing? Okay? If R2 is negative, that means that whatever it's the derivative of must be decreasing. Must be decreasing. Okay? Is R1 getting less positive or more negative? Must be more negative because I showed you that R1 is also negative. All right, so again, R2 is negative, so it's the accumulation function is concave down. What does it look like there? So our rate of change is negative. That means accumulation is decreasing. And the rate of change is decreasing. So what does a decreasing accumulation with a decreasing rate look like? So the accumulation is decreasing and its rate is decreasing. Draw it with your finger. You should have done this. That's a decreasing accumulation with a decreasing rate. Here's the graph. Does it agree with all our conclusions? Okay. So let's look at, so we're talking about now, we're talking about the rate of change, or the derivative of the rate of change. The derivative of the rate of change of x, or the derivative of the derivative. And this is called the second derivative. When you take the derivative of the derivative, it's called the second derivative. And so now, what we used to just call the derivative, we specify as the first derivative. So all those problems you did in the mastery exam, you were taking first derivatives. Okay? Here's some other notations for that. F double prime, y double prime, or this, you would say this the second derivative of f of x. Okay? What's that? The x width. Okay, so those are some other notations for this thing, the second derivative. So here's a problem that we're going to keep talking about these relationships. Okay? So here's a function, and here's what we're going to do. We're going to split up. Everyone's going to do one row in this table by birth month. Okay? So, January, February, birth month. You're going to do this row. March, April. You're going to do this row. May, June. July, August. September, October. November, December. Okay? What you're going to find is, you're going to find the value of the accumulation, the value of the first derivative at the x value, and the value of the second derivative at the x value. So hopefully this is a very, very easy derivative. Even if you haven't passed the mastery exam, everyone should go get this, plus the derivative of the derivative, and then you're going to plug in and get your values. So just do your one row. Be as efficient as you can. Can you get it done in like 1 minute? Two minutes. How about that? Okay, we should have this by now. Check your derivatives, first and second derivatives. Maybe you should check mine. How did I do? Raise your hand if you have your three values already. Okay, we'll just do 30 more seconds. Try to finish. Try to finish. Okay, see if it's right. Check your row. Any disagreement? Are we good? Okay, second task. Here we go, second task. So now, based on the values in the table, we want to sketch the behavior of the accumulation function g in the local area of that x value. So you're looking at the values, you're interpreting those values, make it just a tiny little sketch of what you think g looks like near that x, right around that x value. So go, see what you come up with. Okay, so what I'm showing here for at 0, if we've got a negative first derivative, that means the rate is negative. That means g has to be going down. In fact, we know more than that. What, it's going down 8 times as fast as x is increasing, right? So the output is going down 8 times as fast as x is increasing. But if the second derivative is positive, then it has to be concave up. So we put those two together, and we get, what do we get? Draw it with your finger. Like this. That's what's happening around x equals 3. Does it make sense? It's going up, and, or sorry, that's not right. If you were uncomfortable, that's good. All right, so she's going down, but it's like that. So the accumulation is decreasing, but the rate of change of the rate of change is increasing. So the rate is getting less negative. So actually the rate of the rate is going up. Or it's positive. Sorry. Okay, next one. So here, if the rate of change is 0, we have what we call a pause, right? So the output of G for a moment is not changing. How is that possible if the second derivative is positive? Right, and there's one spot there at the bottom, do you see? Right there at the bottom, where our rate is increasing through this whole thing, but the accumulation pauses for a moment. So we can say it's right at that low point. Right at that low point. Okay? This one. The function is increasing, but the rate is decreasing. The function's increasing, but the rate is decreasing. The function's increasing, and what the rate of change is not changing. That's what that's saying, right? So it's saying that our rate is not changing, but the function's going up. So it's, yeah, exactly. So if the rate is not changing, that's like we have a constant rate of change for a moment. Okay, so there's two different ways that could look like. Right there is a transition point from the rate decreasing and then the rate starting to increase again. For a moment there, the rate doesn't change, stays constant. Right, the rate of change stays constant for a moment. So, but this could also be like this. So the 2 says that the function, the accumulation is going up. The 0 says that the rate is holding constant. Or we have like a moment of linearity. Okay, this is called an inflection point. Okay, what about this one? The accumulation is doing what? Increasing. The rate of change is increasing. Therefore, it's like this. Okay, so now we have, what do we have here? The accumulation is holding steady, it pauses, but the rate also pauses. So the accumulation is holding steady, but the rate is also pausing. So it could be like that, or like there's lots of ways, right? That. Are those the only 2 ways? Yeah, those are the only 2 ways, like that. Is it just more exaggerated? What do you mean? No, it's nothing to do with exaggerated or unexaggerated. So the reason see here, the accumulation is going up. The rate is positive. It's going up. Here, the rate of change is 0. So the accumulation pauses, but the rate of change pauses. So you have see here, it's not horizontal. It's still heading up, even though the rate of change changes from decreasing to increasing. Here, the rate of change changes from decreasing to increasing. Simultaneously, the accumulation pauses, or the rate is 0. It's not about exaggerated or not. It's about that this is still increasing here, and this is flattening out. That's the difference.